Swayam Prabha. Digital India. Educated India.
We are looking at aircraft response to inputs. Inputs are the inputs that we can control, right? Changing elevator, aileron, rudder, and so on. And inputs that is not in our control, right? External inputs. Right. So, we already looked at one simple example where we talked about the response of aircraft in roll to aileron input, right. So, not making things more complicated, we will just stop at that. Now, we will look at aircraft response to external inputs, and these external inputs are coming from the wind, right. Now, wind can have any form which may be known or not known, but what we will discuss here is the form of the wind which is known to us, right. Okay. So, what we are expecting is this extra term accounting for the external inputs, and these inputs are atmospheric inputs. Right. So, what is going to change if you have wind changing? One thing is flying your aircraft in still air, right. Then what you are talking about is these velocities along XYZ axis of the aircraft and the rates, right. These velocities are going to enter into the aerodynamic forces and moments, right. So, if I talk about another situation which is not still wind, not still air, but the air has some velocity, the wind has some profile, right, in space or in time. Now, that has to be taken into account, right, because aerodynamic forces and moments we calculate based on the relative speed, right, relative wind speed, right. Okay. So, if you assume that your gust of wind has some profile, we will denote that speed with this subscript g, right. So, wind has some velocities, it is not still air, and it can also have a profile over some distance, right, which can be larger than the size of the aircraft. In such a case, you will also have gusts which are known as rotary gusts. Okay. Let us see how we can model the wind into our aircraft equations of motion, right.
So what about like double derivatives of velocity? I mean, if there's a sudden gust, we can't model it as a linear.
Right.
So how do we?
We'll look at that, right. I am going to take this gusts as function of time, right, so that you can differentiate it as many times as you want, right. So we are going to look at temporal variation and also spatial variation, right, both. So what is it going to change? It's going to change the relative airspeed, right, coming onto the wind, coming onto the airplane, right. So if delta u, now I am again talking about the linear motion about an equilibrium state, right. We have this linear model where we are trying to model the wind. So absolute delta u is now going to be delta u minus u of g, right. So I am assuming that no, I am putting a minus sign here because this u I am taking in the direction of the x axis, right. This u is in the same direction, so relative airspeed is low, right, if the wind is in the same direction. Similarly, you can also write other components of velocity. This is what now the aircraft is going to see. And the rates are also going to be different, and I will tell you where this change in roll rate due to the wind is coming into, right. Where is this coming from? I will tell you shortly. What is it going to change? It is going to change the stability derivatives, right. In here you have the stability derivatives which are playing role in describing the behavior of the aircraft about the equilibrium state, isn't it. So let us look at how the stability derivatives are going to change. Now this delta u here is the new delta u. Anything else also which changes this force can be included, right. For example, if you have x changing due to the pitch rate, then you have to include this new change in pitch rate in your model. And so on, right. So this we have to do for every derivative. and so on. So, you can write other terms also in this fashion. Right. Now, the question is where this rotary gust is coming from. You understand where this this wind profile is coming. The wind has some velocity, right, and this rotary gust is coming from that wind profile. So, let us look at let us go back to the previous lectures where I was talking about how a pitch rate can introduce a velocity in the forward direction, in the vertical direction, right. So, we had this aircraft which is pitching, and then it can introduce this delta W, right, because it is lying away from the CG, right. So, going by the same argument, you can write this QZ as right. This is the x direction. If you have wind changing in along the x direction of the aircraft, then it can give rise to this pitch rate, which is rotary gust, right. Similarly, you can have a wind profile along the span of the wing, right. So, changing along y, the vertical gust changing along y, and that can give you a rotary gust in roll, right. Everybody gets this. So, look at this airplane from now you are looking at it from the front, right, and you have a profile which is changing along the span of the wing. So, along the span of the wing, this Wg is not a constant, right. If it is constant, then it will not give any roll, right, but if it is some arbitrary profile, is going to give rise to the roll motion, all right. So, because of W vertical wind changing along the span of the wing, we get this PG term, right. Okay. Is it also going to give you yaw? Not really, right. This vertical wind is only going to give you the roll and the pitch. Now, this can also be written in terms of now this is what you were talking about, right. Right, this is what you talked about. Okay. Now, if we include these terms, extra terms in the aircraft linearized model about the equilibrium state, then what you are going to see is this extra term, right. So, let me just write down the equations for the perturbed longitudinal motion. Right. This is what you are going to get after you substitute these derivatives in the original equation. Okay, so this is my original A matrix, which was obtained by linearizing aircraft equations of motion around the equilibrium state, and this is my original B matrix. And this comes because of the wind. So, again if you want to model all of them together, then doing anything analytically is not possible here. So, what we are going to do is we are going to take one simple case and see how you can model the wind into your equations of motion and study the aircraft response to the gust. So, let us say we have this model mounted in the wind tunnel, okay, and we are looking at the motion of aircraft only in the jet direction. Okay. This is the jet direction, and there is some mechanism which allows it to move in the vertical direction, but that is the only degree of freedom it has. Okay. The only degree of freedom. So, this motion is called plunging motion. Okay. The only degree of freedom this aircraft has okay, and you have some profile which is in the vertical direction. Right. We will look at some cases. To start with, let us assume that this is the case. What is it going to change? It is going to change the angle of attack, right, because this velocity is in the vertical direction. So, let us try to look at the motion of the aircraft along z direction, right. So, writing down the equations for the motion is m into dw over dt. This w is the velocity in the z direction, and that is going to be equal to this acceleration is coming because of the aerodynamic forces, right, and the weight of the aircraft. Let us also assume that we study the motion, perturbed motion about a steady state condition, which is this. Okay, so, aircraft is perfectly balanced with the lift, weight is perfectly balanced with the weight in the steady state condition, right. This z naught is minus of L. Now, let us take a perturbation from this condition. Okay. So, we will assume that the equilibrium speed, vertical speed is w naught, and then add a delta w to that, and this is going to change the force in the vertical direction, right. This delta w is going to change this force, and that is how you get the motion from the steady state condition. Substitute these in this equation. Okay, small w's are the vertical speeds, and this capital W is the weight. Okay, so what we get from here is this. There is the linear model, and I am looking at the linear motion of aircraft around equilibrium condition. Now, this force is going to change because of a steady part which is coming from change in angle of attack, and there is another part which is because of change in rate of angle of attack. So, we can write this also as this, right, z alpha into delta alpha plus z alpha dot delta alpha dot. In terms of the coefficients, it is going to look something like this, right. We have to non-dimensionalize this coefficient. So, we are using this factor to non-dimensionalize this number, right, which otherwise will have a unit because of this alpha dot. It is also equal to minus of CL alpha minus of CL alpha dot. Now, what is this delta alpha? Delta alpha is this delta alpha is absolute delta alpha, right. So, how we are going to write it in terms of including the gust. So, that delta alpha is delta alpha relative, which is equal to delta alpha earlier and including the alpha coming from the gust. Right. This is how we have written small angles of attack in terms of the vertical velocity. Okay, so now go back to that equation and assume that this term is small, so that we can further reduce our model to a simpler one. You can also go back and just write this as z alpha. So, what you have is remember what we are assuming here is that this z alpha dot is negligibly small and we can ignore the second term. So clearly this term is appearing as a input term which is not under your control, right. You can only define some particular variation and look at the dynamics of aircraft in the vertical direction, in the plunging motion, right. If we do not have any knowledge of this WG, then you have to go for example turbulent models, you have to go for higher level mathematical techniques to find out the response. But here we will look at some simpler models for this wind and see the response of aircraft to that motion, gust. So call this this is like a time constant, right. If you set this equal to 0, this is giving you the free response, right. WG here is appearing as an input which is almost same as the control input in case you have the knowledge of this, right. It is acting as an input. So call this tau, which is the time constant of the motion, and try to solve this equation. We already solved one such equation in the last class. So we used what is known as Laplace transform technique. We will apply that to this problem as well. Right. The advantage here is that it converts a differential equation into an algebraic equation, right, and you are more at ease solving algebraic equation than solving a differential equation. So this is one big advantage of using this technique, and it is applicable only to linear models. Now let us look at a profile of this WG, and it is looking something like this. So your aircraft is going in this direction and suddenly it sees wind in the vertical direction. Okay. So it is like a step input, right. So let us say that this amplitude of this step is AG. What is the WGS for this step input? We have to take the Laplace transform of this time variation. So this is a step, or so vertical gust uniform, it's just going to look like a step input, and unit step input, if you take the Laplace transform of that, it is 1 over s multiplied by this amplitude. Now let us try to solve that equation, write it in time domain. Okay. So, take inverse Laplace transform of this now, and you have found your solution in time domain. You can also calculate the normal acceleration from this by integrating it or differentiating it with respect to time, and that is going to be right. That is the normal acceleration of the aircraft because of the gust. When is it going to be maximum? It is going to be 0 at steady state, right, but it is going to be maximum at t equal to 0. This tau, which is the time constant, is this, right. This Z alpha is nothing but the minus of L alpha, right. Z is in the negative direction, or Z is this direction is the vertically down is the positive direction, right. So, left is acting in the negative direction according to the choice of axis system that we have. So, Z alpha is minus of L alpha, right. So, let us expand that. So, Q S to C L alpha over u naught into the amplitude of the gust. And there is one m also here. Right, whenever we write z alpha, we are taking m as the factor, right. We are dividing, so this z is Cz q into s. When we write z alpha, we write it like this. That is where this m comes from. So, we can find out the relative magnitude of this acceleration with respect to g. And this is nothing but delta L over W. Okay. Can you see that? So, if you just balance these two, what you are going to get is m into delta W dot, and that is coming from the change in lift, right. So, corresponding to this, the load factor, there is a change in load factor which is delta n, right. L over W is the load factor, and the change in lift is going to cause a change in the load factor, which is giving the acceleration. Okay. So, this load factor is going to be a function of change in load factor is a function of CL alpha. I am expanding this q, which is half rho u naught squared. So, this acceleration is definitely, from this formula you can see that is going to depend upon how your wing loading is, right. High wing loading means low acceleration because of the vertical gust, right. Low wing loading, high acceleration at any particular speed. This is the equilibrium speed, right, forward velocity. It is going to depend upon what is the wing loading. Where do you see the wing loading low? Which aircraft will have low wing loading? Transport aircraft. Aircraft which needs short takeoff and landing requirements, they are usually having low wing loading, right. Short takeoff and landing requirements results in low wing loading, or you can make statements other way around as well, right. So, in such a case you are going to see larger acceleration because of the wind. For aircraft with, so this is clearly related to the landing and takeoff performance of the aircraft, right. landing and takeoff performance requirements of the aircraft. So, a short takeoff and landing aircraft designed for this case will have low wing loading, and in such a case you will see larger acceleration due to the vertical gust. So, this is one useful inference we can make from this analysis, and this is for a very simple case when you are only looking at the plunging motion, right. What we will do in the next class is we will look at another profile, right, again in time, but the wind may be varying also spatially, it is not just a temporal variation. So, how are you going to model that is in your aircraft equations is also something that we will talk about in the next class. Right, we can stop at this point.